Good evening, everyone, and welcome to this evening's Fire and Safety Division Engineers Ireland CPD event. We have two gentlemen from Jensen Hughes offices, and they're going to be given a talk on structural fire engineering. I'm going to hand you over to Gordon, and he can introduce the other presenter. Thank you very much.
Thanks, Sinead. Just by way of introduction, I'm Gordon Morley. I'm a director of Jensen Hughes Ireland, fire safety consultants based in our Galway office. We also have Irish offices in Dublin, Cork, and Belfast, as well as the wider UK and European team. Thanks for joining us for this online CPD session on structural fire engineering for innovative design solutions. So the presentation will be given by my colleague, Mikko Salminen, who is our structural fire engineering lead for Jensen Hughes Europe. And Mikko is based in our Finland office and has a PhD in structural fire engineering and 20 years experience in the performance-based analysis of structural fire safety. So without further ado, I'll hand over to Mikko to present the CPD.
Thank you, Gordon. And good evening, everyone from Finland. I'm Mikko from Tampere, Finland. And first, I want to thank this opportunity to talk about one of my favorite subjects, structural fire engineering. So first, about the contents of this session. So first, short introduction. This is probably quite new for many of you. So first, what do we mean when we talk about structural fire engineering? And then moving to more detailed stuff like different kind of structures, because steel, concrete, and timber behave and perform totally different way in fire. So we will talk about steel structures, composite structures, timber structures, and then moving to structural details, which is something that we work a lot, and existing structures also, and finally few case studies, also a couple of case studies from Ireland to show what kind of or where structural fire engineering can add values for the project. So first, short disclaimer, as we are US-based company. So I'm not going to read all this through, but I'll leave it here for, say, 5 to 10 seconds so you can take a look at it. So this is something we need to show. Okay, I think you had a chance to read it. And we can move the introduction of structural fire engineering. So I assume that many of you have some kind of understanding what is structural engineering. It's of course dealing with loading of the structures and strength of the material and the material performance and structural resistance. My background is structural engineer, but I have been dealing with fire more or less 20 years already. So I think that's good background for structural fire engineering, also because structures perform more or less the same way in fire than as they do in normal temperature. Also, of course, there's some differences which we will talk about in detail later. But good understanding how structures perform in normal temperature is kind of required in structural fire engineering. And perhaps many of you also have understanding of what fire engineering means. So it's more dealing with the fire safety in buildings, like compartmentation and egress, and making sure that the buildings are safe enough in a fire situation. And often it's based on prescriptive regulations, like checking from the tabulated data, which is what is the requirement for this structure. And it often depends on the type of the height of the building and things like that. So structural fire engineering is some kind of intersection of these two, and in my case, my background is structural engineering, and I have a lot of colleagues in my team who know more about fire engineering, like determining realistic fire scenario for different buildings and so on. A couple of examples of structural fire engineering. So it can mean many different kinds of analyses depending on the case. First, the one on the left upper corner, there's a so-called standard fire, ISO fire. So the black dashed line is the standard fire curve, which is like mostly used in the fire design of structures. It's over 100 years old, so it's not a new invention. But of course, we need some kind of standardized fire curve, so we can say that this structure is better than this one. But it's not based on like actual fire scenario. It represents at some level like a flashover fire in small compartment. But in many buildings, that it is not realistic fire scenario. So we have one example here, this compartment fire curve. So the Eurocodes, for example, they have a parametric fire curve or model where you can take into account the properties of the compartment and the actual fire load in the compartment. So that's one simple example of more realistic fire curve. So you can see that the temperatures are a little bit higher than in the standard fire, but there's also a cooling phase, like in all realistic fires. And in standard fire, there's never going to be a cooling phase. It's just temperature just increases and increases. That's one way to apply structural fire engineering in projects. And the illustration on the right top corner, it is actually from Tampere, my hometown. And that's a case where we analyzed steel trusses because the prescriptive requirement was 1 hour fire resistance in standard fire. And it was clear that it's not realistic fire scenario for them. And there's no fire load close to the steel trusses. And we did some fire simulations to show that for the authorities also. And the end result was that there was no fire protection needed for the steel trusses. A couple of other examples, some thermal analyses of some detail. We will take a look later in more detail, and some structural analysis about the deflections of the structural system in fire. So we have a lot of different kinds of structural fire engineering projects going all the time. Some of them are really small ones where we analyze some detail, and in some projects we analyze full structural frame. And now moving to important question, why to apply SFE in projects? So there's of course a lot of benefits, and it's of course not secret that usually the main driver is the reduction of cost. So it's quite obvious that if we can optimize the fire protection, it means also optimizing the costs. But there's also a lot of other benefits. So, for example, I'm not going through all of these, but for example, long-term maintenance. If you don't need any passive fire protection, so you don't need long-term maintenance for that also. And it can save some timelines in the construction also. Also, usually the prescriptive code and the building regulations, they are based on prescriptive regulations, which are based on like traditional systems, and they don't really take into account anything new, innovative designs. So in structural fire engineering, you can model the actual structure and take into account what's the performance realistically. maybe a couple of more I want to mention. So if you do full-scale structural fire engineering, you get an understanding of the structural fire, how it's going to actually perform in a realistic fire scenario. And if you do the prescriptive design, like using standard fire for individual members, you don't really get any understanding what is the realistic performance in fire. But with this more realistic model, you can really see what are the deflections in fire, what are the weak points of the structure, can we optimize something in some areas, and on the other hand, do we need to increase protection in some areas to make it more safe? Okay, then moving to different materials. So starting from steel structures. Steel structures are often applied in structural fire engineering because usually they have only like 15 minutes fire resistance in standard fire as unprotected. And that's why they often need some applied passive fire protection to achieve 30 minutes or 60 minutes or whatever higher classification. As you probably know, steel and like other metals, they have high thermal conductivity. They are often quite thin-walled elements. So as a result, they heat quite fast. As I mentioned, like something like in 15 minutes, they might get like 500 degrees average temperature in the cross section already. But on the other hand, steel structures are widely used in large-scale buildings, which have large spans and so on. And the steel structure may locate quite high from the ground. So it means that the fire load, especially in the cases where there is low fire load in the building, the fire load may locate far from the structure. So that kind of open up some possibilities for structural fire engineering. There's a couple of examples here. I think all of these are from Finland. So in these cases, we have steel frame and we have modeled the fire, which is localized. And as you can see, the actual fire is quite far away from the roof structures. So the model gives us the temperatures that are affecting the steel structure, and we can make some conclusions from there that the critical temperature is not exceeded. It's quite typical assumption that the critical temperature of steel is around 550 degrees. And usually, if you don't have any calculations done or anything, it's quite safe, good approximation. But for example, in Finland, the structural engineer in the project usually calculates the critical temperature in detail because it's not so difficult task. So and there's some optimization to be done that can be done for all the elements, because if you have higher critical temperature, then you can optimize or reduce the fire protection. So that's something to think about also. It's not always 550 degrees. If you use Eurocode methods, for example, you can get sometimes to 600 or 650 or something like that. Okay, then moving to composite structures, and with composite structures, I mean here steel and concrete. I'm not sure how typical structural system in composite structures is in Ireland, but in UK it is quite typically used, where you have steel primary beams, steel secondary beams, and then metal deck with concrete. So that's a really good structural system for fire, because often it performs much better as a system than the simple methods would predict for the individual members. And that kind of gives an opportunity to reduce the fire protection in some of the members, especially in the secondary beams. So even if the deflections are high in the structure, it still has the resistance if it's designed correctly, like this one here. So we have here a unprotected secondary beam in the middle of the span, and then it could be justified that it works okay as a system. But if you would only do some hand calculations, you wouldn't make this work. So sometimes it's useful to model larger system where you take into account the primary beams, secondary beams, and the whole deck system. And then moving to timber structures. So timber structures has been quite hot topic in fire engineering and especially in structural fire engineering for some years already, which is quite natural because it's been more widely used, especially in Finland and I'm not sure about Ireland, but in Finland and in Europe generally and in US, it's been more widely used, and there are design methods available, but sometimes the guidance is quite vague and it doesn't tell you exactly what you need to do structurally with timber, that it's okay. So of course we all know that it's combustible material. The fire resistance is usually based on the residual cross-section, so it chars a little bit, but you still have some residual cross-section where you have most of the strength left. But structural fire engineering may be needed in many cases to justify the use generally as a load-bearing structures, especially if you have a large building. Usually the regulations don't allow to use timber there unless it could totally encapsulate it. So structural fire engineering can be used to justify at least some elements there, that this structure has the capacity required for the full fire scenario, even though it's going to burn there and it's combustible material. One thing that is challenging with timber is connections also, or it might be challenging if it's not fully inside the timber, because when you have steel going inside timber, it conducts heat there. Even if it's intumescent painted, it may conduct a lot of heat inside the timber. So it's sometimes challenging with connections. The good thing in Eurocode standards in the new revision is that there will be a lot of updates related to timber structures, a lot of new methods available to design timber structures structurally for fire. They are sometimes quite challenging methods to use and require a lot of expertise, but still it's good that there's methods available. And these figures here are from my colleague's master thesis a couple of years ago. We did some fire testing in Tampere University, Finland, for CLT slab, so cross-laminated slab, cross-laminated timber slab, and in this case we didn't use standard fire curve. We used this fire curve, which is shown on the right-hand side. So it goes according to standard fire up to 34 minutes, if I remember right. But then we have a cooling phase because we wanted to investigate the case more realistic fire scenario and the failure in the cooling phase, because with timber you may have often the failure in the cooling phase, and actually in this case the failure occurred something like after 4 hours. So we had to wait quite long there. Even though the temperatures are really low already, it's in Finnish, sorry. But at 180 minutes, we have like 100 degrees only in furnace. So it's like Finnish sauna at that time. And 1 hour later, it failed. So it's really challenging and interesting behavior. But it's because even though you have cooling phase in the furnace, the timber cross section continues heating more hotter. So that's really interesting behavior. And the good thing there was that we were able to model it quite well, and the prediction, we did the models beforehand, so the predictions were quite good in this case. So we were able to model the failure in the cooling phase and with some safety margin also. So that gives us confidence also to use these methods in real timber buildings. And then moving to structural details. This is something that we do a lot, and it's because you cannot test every variation of all details. In real projects, there will be different kinds of fire protection details because of many reasons, and especially in UK, often an assessment is needed from fire engineer to assess if this detail is at least equivalent as the tested one. So in many cases, we do some kind of model where we can compare the proposed detail with the tested detail. So we can address the deviation there. And if it doesn't work, we can propose some more protection, for example, or something like that. These examples here are related to compartmentation. For example, the one on the left, where we have a steel beam inside a concrete slab partly. So there was a question about how much the steel conducts heat to the upper. Oh, sorry, in this one, the fire is on the top floor. So how much the steel conducts heat to the lower compartment, and we could conclude that it's within the limits of the acceptance criteria in this case, and the same question basically was asked in the models on the right, but these are wall structures. So these are quite typical where this kind of thermal analysis can add value, and there's no need for fire tests. Of course, it's really important to calibrate the model well. So if there's any test data for something similar, we always try to calibrate the model so that it gives the same results as in the test before moving to the model with deviations. Okay, then moving to existing structures, they are also quite typical projects that we do, and that's because often the fire resistance of the existing structures is not known. It's not documented, or basically the structural engineer cannot tell how many minutes in standard fire this structure achieves. It's also often quite challenging even with structural fire engineering methods, but we can again try to calibrate the model with something if we have something similar tested, and then based on the surveys we can do a model and estimate what would the expected fire resistance be. But it's definitely more challenging than with new structures, because there are some more parameters that we cannot know of course, we need to rely on the results of the surveys and so. And then moving to case studies. So, as I mentioned, I have a couple of case studies from Ireland. So this one is industrial project and existing building which had a sprinkler system, which is really reliable system usually, and especially in this case, they really had more reliable system than usually. And per prescriptive design, they would have needed to protect many steel beams there, but for some reason they hadn't protected those, and we investigated if we could justify it in some areas. So because it would have been really challenging to protect them at that stage of the project. And so we investigated how much can we rely on the sprinkler system, and if the sprinkler system doesn't operate, what would happen then? So the process was first doing some fire simulations, like shown here in the figures. The actual fire load in many of the compartments was quite low, and the figure below shows some fire simulations or a fire simulation model for cable fire, where the cable racks are like below, or cable trays are below the steel beam. So that's the worst case scenario, and we had as much cable as possible in the model. And there's a lot of fire tests done for the cables, so we were able to calibrate the model to that. And the fire load and the fire or the heat release rate coming from the fire. So that's the fire side of the problem. Okay, here you can see the simulation when it was running. So we basically got the temperatures affecting the steel structure there, and we were able to calculate what is the temperature in the steel profile. They were quite massive steel profiles, so they wouldn't heat that fast, which helped also. As a result, we could conclude that most of the unprotected beams in this case, they could be justified without compromising the fire safety. And one of the reasons was really reliable sprinkler system, which was taken partly into account in the analysis. So we did analysis with the sprinkler system. If it operates, there was no structural failure in the location. And that's usually the case when a sprinkler operates as it's designed. But we also, I think we need to always account that case where it doesn't operate as designed, at least at some level. So we analyzed that case also and concluded that there's no premature structural failure in those cases also, to make sure that all the people can get out of the building, and also leaving some time for the fire brigade operation. And this one is also industrial project from Ireland, a little bit different challenge here. So again, this was existing building, and this item or authority had raised this question and some time ago, and there was some back and forth about it, and then we concluded that maybe some structural fire engineering analysis could help to solve this problem. So they raised the question whether the steel beams conduct heat through the compartment walls. And the steel beams were protected 1,500 millimeters from the wall on both sides. I think that's some regulation, based on some regulation in Ireland. but it would have been challenging to fire protect it more or box it out some way. So we investigated the existing situation and wanted to check if this design can achieve the compartmentation criteria. So we did again fire simulation model, and again the fire load was really low, and there was not much openings in the compartments, so the fire wasn't actually really bad. And then we did the thermal model of the beam with the fire protection at the 1500 millimeters, and did the thermal model, and the result was positive that the proposed design achieved the required separation criteria with quite clear margin. This one is existing structure, a hollow pot slab from UK. So it is historic educational building, and the fire resistance is unknown for this case, and the requirement is 1 hour. So we have the structural requirement for 1 hour and also the compartmentation. So we did the analysis with and without plaster. So first without the plaster, and if it didn't work, then we did also with the plaster below the structure. So the first model, we concluded that yes, we can achieve the insulation criteria, but the strength of the main rebars is only 65% of the normal temperature value at 1 hour. And based on the structural calculations, we needed 67%. So it was quite close. But of course, with the existing structure, we also want to have some safety margin. So we concluded that in this case, the 10 millimeter plaster is needed below the structure to limit the rebar temperatures. And with that, the strength of the main rebars was full 100% of the normal temperature strength at 60 minutes. So it was clear solution for this case. And in the beginning, I showed the parametric fire curve, which is quite simple method to estimate the fire but in more realistic way than the standard fire curve. So in UK, we did parametric fire analysis. We have done it for many buildings, but this one is 10-story office building, but it's renovated to an apartment hotel. And parametric fire works really well in small compartments where you can assume that the temperature distribution is more or less uniform in the compartment. It doesn't really work well if you have full open office area, because then you may have traveling fire moving all around in the floor. But in small compartments, like in this case, parametric fire curve gives relatively good estimate for the temperatures in realistic fire scenario. So the problem here was that the structural engineer had confirmed that the slabs achieve 90 minutes fire resistance, and now the requirement would be 2 hours because of the renovation and change of occupancy. So what we wanted to do was to investigate if this 90 minutes rated. So this 90 minutes always refers to the standard fire. So if this 90-minute rated structure would survive full realistic fire scenario, that's what we wanted to investigate. So we did again the fire simulations or the parametric fire analysis and thermal modeling of the slab structures. And the results are shown here. So the figure on the right low corner, bottom corner shows the final parametric fire curve. And you can see that the heating phase of the fire is around 40 minutes or so, and the maximum temperature is below 800 degrees. So it's below the standard fire curve in this case. And of course, you have a long cooling phase, but the temperatures are not that high anymore. So that was the design fire curve for our case. And then we used this fire curve for the structure and concluded that the reinforcement has again full 100% of the full capacity and for the full duration of the fire. So we can expect that it survives the full fire scenario, not just 90 minutes or 120 minutes, but full fire scenario. So there was no need to underboard the soffits here. And this, I think, is the last case study. So a mass timber office building from Finland. And this one has 8 stories. It's still in preliminary design phase. Actually, you could design 8 stories timber building in Finland using prescriptive regulations. So basically, you wouldn't need performance-based design or structural fire engineering. But in this case, there was many reasons why some more detailed and advanced analyses were used. Compartmentation, for example, and also that the client and architect wanted to have some exposed timber surface. The columns and beams fully, and also around 30% of the CLT slab. So that, of course, increases the fire load when it's not encapsulated. And that's something we need to take into account in our analysis. And this is the figure in the middle is a fire simulation model of one floor in the area where we are able to take the timber surface into account when it ignites. So it, of course, increases the heat release rate and fire load in the compartment, but it can be and it needs to be taken into account. Our preliminary requirement for the structural engineer was that he needs to design it to 3 hours. That's of course sounds quite a large requirement, but actually the size of the elements was quite large also, so it wasn't mostly a problem because they have quite good inherent fire resistance. So we did those fire simulations, and in this case, you can see from the top right corner the temperatures. They go now over the standard fire curve because of the additional fire load. So this is basically for one location. This is not for the whole compartment. This is only one location because the fire moves all around in the office floor. But this is for one column, the maximum temperature. And you can see that it goes really hot, much over the standard fire curve. But on the other hand, the cooling phase is quite fast also. So it's quite peak there. But this is we got this result from the fire simulation, and we're able to use it in the thermal analysis. And once we analyzed the cross section of the column, then we were able to transform that into the structural model to take into account the residual cross section, which hadn't charred in timber, and also take into account the reduction in strength all around in the timber column, which is especially in the cooling phases, which is really important that we take into account the strength reduction also. But we were able to show that this one has the required capacity also during the whole cooling phase. Like I showed the fire test result earlier, the CLT slab didn't survive the full cooling phase, or it survived like 4 hours, but not more than that. Okay, I think that's it from me, and now I think we should have some time for questions also.
Thank you very much. That was interesting, and I like the way you presented the different cases. You understanding the basis of the different materials across the board there, and from a UK, Irish, and your own home country experience as well. There are a few questions there. I'm going to start off with software packages that you might utilize in your own analysis. What are the different packages, and do they vary across the different materials that you are analyzing?
So, sorry, I couldn't hear all of it. So,
what are the different structural software packages that you might
software
use?
packages? Yes. Okay. So, in fire simulations, we use mostly FDS, but it's not like structural software. But in thermal analysis and in structural analysis, we use Sapphire. It's developed in Belgium, Liège, I think like 30 years ago already, and they do really good development of the software all the time. So it's Sapphire, SAFIR, and I think it's might be the most widely used software in structural fire engineering. There are other softwares like Vulkan in UK from Sheffield University. And of course, you can use like some multi-purpose softwares like Abacus, Ansys, but they are not. Sapphire is good because it's designed like tailored for fire and structures only. And it also has the material properties and so on within it.
One of the participants are looking to see if you use a software called ANSYS, ANSYS software for fire simulations and structural analysis. SYS.
Oh, okay. Yeah, I know it can be used. I haven't used it, but I think it's more like multi-purpose software where you can analyze pretty much anything with that software. So it might be pretty expensive compared to software what we are using, and you don't need all the modules in structural fire engineering. But I think I have seen analysis that have been done with that software also.
Another question here with reference to case study 1. So where passive fire protection could not be applied to all members, was a structural analysis covering both resistance and stability checks carried out in parallel with fire simulations?
Yeah, we did we did the fire simulations first, and we got the temperature profile for the steel beams. I'm not sure what is meant with stability analysis here. So we did some, again, Sapphire analysis where we made the structural model of the beams. So it was mainly related to beams, and they were quite stocky beams. So basically there was no like stability issues, but we checked that they perform well enough in fire and they don't fail in fire. But basically if you do the Sapphire analysis, structural analysis, you can take into account the stability failures also with that.
Okay, same type of question again, but they want also to know, were realistic accidental fire loads combined applied in the engineering assessment rather than constructive fire loads assumptions. I suppose they're questioning whether what assumptions were you using in your assessments in terms of fire load?
Yeah, that's a good question. Well, for example, for the parametric fires, like for compartments, there's quite good guidelines in UK and in the Eurocode. Eurocode has some values for, say, different occupancies, how much fire load there is, and we usually use the at least 80% fractile. So we need to be on the safe side, of course, because you don't know exactly how much fire load you have. There might be an apartment, but the UK guidance gives kind of good framework for that. It gives the values of the fire loads, and then it also gives what is the target reliability also for different kind of structure or building, depending on the height, for example. So that's where it comes from. But on the in different kinds of projects where you have like localized fire load, then we need to usually find the information from literature, like for the cable fires. But the good thing is that there's a lot of fire test data available around the globe. They have tested, for example, cable fires in the US a lot. So there's literature available. So we can take it from there and then assume that if you have maximum amount of cable in here, how severe is the fire?
Another question there, I suppose somebody's looking to see if you have any experience in dealing with post-tension slabs in buildings.
Yeah, we have some experience, and well, the experience is that they are quite challenging to model. They can be modeled, and we have done some work with them, but it's if you compare like regular concrete structures, it's much more challenging, and you need the calibration of the model might be challenging. It can be done, but so far the results that we have got from the calibration are maybe a little bit too much on the safe side. It's of course good thing that they are on the safe side, but it's really challenging.
Next question is in relation to secondary beams. If they are unprotected or less protected, how does one ensure that their displacement does not cause the connection to damage the primary frame or beams and weaken the overall fire resistance?
Yeah, okay, that's also a good question. Yeah, I mean it requires some discussion with the structural engineer. How much deflection can we accommodate in the structure, or what rotation can we accommodate realistically there, and then we need to compare our models. It's like usually in this topic and in other topics, it's cooperation with the fire engineer, structural engineer, and with the structural fire engineer to make sure that we have the right acceptance criteria set for the structure, like for example the deflection and the rotation of the connection. And yeah, that's it pretty much.
Okay, probably a very open-ended question this one is, but in relation to the second generation Eurocodes and the standard EN 1995/1/2, what should we be looking for? Me being a layperson, a non-structural engineer, what should I be looking for if I open up that code myself? Any recommendation?
I think yeah, we have a master thesis going on about the topic at the moment. So I think it just gives much more opportunities, like to take everything into account. So if you have like a floor structure where you have boarding, insulation, different kinds of timber members, so it kind of gives you opportunity to take like everything more realistically into account and different factors compared to the previous version of Eurocode. It didn't have that many methods, but I have to say that I have some learning process still with to do with the new Eurocode.
Okay, perfect. My own question is probably just going to be a simple one. Your assessments or your employment on various projects, are you finding there's a lot more of new buildings or reoccupation of existing buildings that you're getting involved in?
I would really say that both. Of course, we get a lot of like the one of the examples of the case studies was where the occupancy was changed. So often if the occupancy is changed, then you may have different requirement for the structure. So then there might be a need for structural fire engineering. So that's kind of something that yields to more to existing buildings, but I would say that we would like to be more involved in the early stages in new projects, because in that way we could maybe add more value in the early phases and start the optimizing process, because once you have almost everything done, it's hard to optimize anything unless there's some like a mistake done on the site and we need to prove that it still works. But it would be good to be involved in new projects earlier.
Yeah, fair enough. And just the last question then, again, maybe a simple one, but all depends, depending. Where's the future in all this lying, basically? Are we going taller, denser developments, industry, larger compartment sizes? What's trending, do you see, into the future?
Yeah, I would say hopefully I would like to see structural fire engineering used like more like a almost everyday tool in projects generally, because it kind of gives tools to rationalize the fire protection in many cases and use the resources where they are needed. So that's what I'm hoping for. But of course, timber structures are the hot topic, as I mentioned. And it's compared to, for example, to steel and composite, it usually requires much more work from fire engineer and from structural fire engineer. So that's something probably we are going to be working a lot in the future.
Okay, perfect. Thank you very much. I'm conscious your colleague Gordon is sitting there lovely in the background. He's even muted himself. This is great. Thank you very much, Gordon, for arranging, and for Mikko as well for coming on this evening and giving a presentation. It was enlightening, always especially helpful when I learn a few things along the way as well. So much appreciated, gentlemen.
No, thanks very much, Sinead, and thanks, Mikko, for presenting.
Thanks for the opportunity.
Thanks, lads. Good evening to you, and we'll talk again.
Okay. Take care. Bye, everyone.
Slán.
Thank you.